Okay, in the previous lectures, we talked about principal component analysis, and we learned that principal component analysis is a way to capture the direction of maximum variation in data. Today, we are going to start a new topic, which is Fisher's linear discriminant analysis, and in short, we call it FDA. As I mentioned the other day, in some papers and some books, you may see the term Fisher's discriminant analysis for LDA, for linear discriminant analysis. But Fisher discriminant analysis in this lecture is a method of dimensionality reduction. It's not a method of classification. But LDA, linear discriminant analysis, is a method of classification when we assume that class conditionals are Gaussian. So we learned that in PCA, the first principal component captures the direction of maximum variation in the data. So suppose that I have data in this form. So PCA most likely will capture, a direction like this, which is along the direction of maximum variations of this data. Okay. Suppose that I want to do classification, and suppose that these two clouds of data are coming from two different classes. So this is not from the same class as the other one. So this is a different class. Or let me just do it this way, This is one class, and this is another class. So the direction of maximum variation may not be the best direction for classification. PCA is blind, has no idea about labels of the data, makes no distinction between black and blue. All points, all endpoints are the same for PCA. PCA just look at, it's unsupervised method. Just look at the direction of variations. But if I provide more information to my model and tell the model that, okay, see, I have all of these data, but this part comes from one class, this part comes from a different class. I want to project the data in one-dimensional space, but this is for the purpose of classification. It's not for the purpose of, capturing the variation of the data. If that's the case, then the best direction may not be this direction, the direction of maximum variation. The best direction, for example, could be this direction. If I project everything on this direction, then all black points will be here, and all blue points will be here, and then I can make distinction between them. I can feed a classifier using this one-dimensional points now. Okay. That's basically what FDA does. FDA is a method of dimensionality reduction, but for the purpose of classification. It's supervised. It uses the labels of the data. So when I have these two clouds of data, suppose that I want to project it in one-dimensional space. Intuitively, what can I do to have the best separation? I have two clouds of data. I can collapse all points of this class to one point and collapse all points of this class to one point, another point, and then take these 2 points as far apart as possible. Okay? That would be an ideal case. If I have a projection which collapse all of the points in this class, collapse all of the points in this class, and takes these 2 points as far apart as possible, that would be the best scenario for classification. I make maximum distinction between these 2 clouds of data, and then I can feed it to a classifier and do a good job. That's what we want to do with FDA. Basically, FDA, or Fisher discriminant analysis, is a method of dimensionality reduction it's a method of dimensionality reduction that project the data in the direction of maximum separation. So it projects the data on the direction of maximum separation. Okay? And okay, to do this, first assume that we have only 2 classes. So suppose that I have only 2 classes, class 0 and class 1. So y could be either 0 or 1. And I have n data points. And I have n labels, which are either 0 or 1 in this case. Okay, in this 2 class scenario, I want to project everything on one-dimensional space. So we would like to points to one dimension. So basically, I'm looking for a projection W. So I'm looking for a projection W, and W is just a vector, such that W transpose X is just a scalar. So here X is d-dimensional, and W is also a d-dimensional vector. But Z is a scalar. Then I want to use Z for classification. Okay? But Z, this projection should be a projection which separate these 2 classes as much as possible. Means that collapses all point in one class and then take these 2 classes as far apart as possible. So if I apply a projection to a data point, what's going to happen? So So I apply this projection to all data points. What's going to happen to the mean of these points? So suppose that mu0 is the mean of one class, and mu1 is the mean of the other class. So basically, mu0 is 1 over n 0 sigma of all xi when yi for all i's such that yi is equal to 0. And n0 is the number of points in class 1 or class 0. And mu1 is the mean of the other class. Okay? So if I project all points to the direction of w, what would happen to mu0 and mu1? Mu0 will be, if all points are multiplied by W transpose, mu0 will be multiplied by W0 in the projected space as well, right? The mean of points in the projected space would be W transpose mu0 for this class. And the mean of the points in the projected space for the other class would be W transpose mu1, right? Is that clear? Okay. So now I have suppose that I have W, I projected all points on W. Now, two things. First, I wanted to collapse these two set of each class to one point. And then I wanted to take them as far apart as possible, okay? So let's take care of these two. So goal 1, minimize the variance of each class. Means collapse points, okay, as much as possible. And 2, maximize the distance between projected means. After I projected everything in this direction, I want to maximize the distance between them. I want to take them as far apart as possible. Okay, so let's start with the second goal. So the first class has been projected to direction of W. So the projected mean is W transpose mu0. Second class has been projected to direction of W. So the mean of projected points in the second class would be W transpose mu1. Now I want the distance between these projected points to be maximum. I want them to be as far apart as possible through this projection, okay? Okay, so look at this quantity, W transpose mu0 minus W transpose mu1 squared. This is basically W transpose mu 0 minus W transpose mu 1 transpose W transpose mu 0 minus W transpose mu 1. Okay? I can rewrite this expression in this form. I can take this W out of the bracket. And this W transpose out of the bracket. So I can write it as mu 0 minus mu 1 transpose W transpose mu 0 minus mu 1. Okay. I can rewrite this expression in this form. Do you agree with me that these two are the same? What's the dimensionality of this? 1 by 1, it's a scalar, right? This is 1 by d. This is d by 1. This is 1 by d. And this is d by 1. So it's a scalar distance between these 2 points, right? I mean, if it's not clear to you that these two are the same, it's a scalar. Put a trace in front of this. A scalar, trace of a scalar is a scalar. And then you can rotate elements inside the trace. And you can get this. Okay. Okay, this quantity is known. And the only unknown part is this part, W. Because I know the mean of each class right at the beginning. This quantity which is known, I call it SB in terms of notation. And call it between class covariance. It's a D by D matrix. See, this is D by 1. This is 1 by D. It's going to be a D by D matrix, SB. I call it between class covariance. It captures the covariance between 2 classes because we are looking at the mean of class 1 and mean of class 2. Okay. Times the mean of class 1 minus mean of class 2 transpose. So it makes, each of them are D by 1 vectors. So this is D by 1, and this is the transpose of that is 1 by D. So it makes a D by D matrix, which captures the covariance between 2 classes. Okay? Is that clear? Okay, so we know that when we project points on the direction of W, the mean of projected points will be W transpose the mean. What about the variance or covariance? If class 1 has covariance matrix sigma null, and class 2 has covariance matrix sigma 1. After projection, what would be the variance of points in class 1? What would be the variance of projected point? You know, the covariance matrix of class 1 was sigma null. Then I projected all points using W transpose. Now, what is the variance of projected point? Yes?
W sigma 0 W transpose?
Exactly, or the other way around. W transpose sigma W. It's, we had this in PCA as well, do you remember? The same thing will happen here. That would be the variance of projected points. Okay, so that's variance of projected points in each class. Okay, I wanted to look at the goal 1. We wanted to minimize the variance of each class. So basically, I would like to minimize the variance of first class after projection. You know, I want to collapse all points in this class to one point. Means that I want to minimize the variance of points in this class. I want to minimize the variance of the other class as well. So can you suggest an objective function which basically I can work with that objective function and find W, which minimizes these two terms? Yes? Just add them, right? So add them and try to minimize it. So I can simplify this. So it's going to be W transpose sigma null plus sigma 1 W, which I want to minimize. Okay? These two quantities are known. So I'm going to show it by SW and call it within class covariance. Okay, to satisfy goal number 1, I have to minimize W transpose SWW when SW is known. To satisfy goal number 2, I have to maximize W transpose SBW when SB is known. So basically, I have to maximize W transpose SPW, and I have to minimize W transpose SWW. And SB and SW are not. So how can I do this simultaneously? You know, I want to do both of these two at the same time. find the W which maximize this and minimize this. Yes?
You maximize the division.
You can maximize division, right? You can basically divide these two and try to maximize this. Is there any other way to do it? Yes?
Can you use the first term minus the second term?
We can do first minus the second. Right. That's another way. You can do this minus the second term and try to maximize. Better to put a coefficient for the second term. Okay. Do these two alternatives get to two different solutions? Let's see, actually. Let's see how this goes, and then we can think about the other suggestion that we had here. So one way actually to maximize the first one and minimize the second one is to maximize the ratio of these two. Okay. So it's a standard optimization problem. It's called Rayleigh quotient. It happens quite often. Do you know how can we tackle this problem? Okay, this problem is in fact equivalent. This is equivalent to this problem. Maximize W transpose SBW subject to the constraint that W transpose SW W is constant. Intuitively, it makes sense. You know, you have a ratio which you want to maximize. When you want to maximize, you have to maximize this quantity and minimize this quantity. Right? So instead of maximizing this quantity and minimize this quantity, let's fix denominator and try to just maximize this quantity. Right? Because similar to what we had in PCA, don't forget that W is a vector, you know, and I can make it as large as I like. So similar to the problem that we had there, that we need to put a constraint to make the problem well defined. You know, it's not exactly the same, you know, because it's not just you know, this SW gives sort of implicit bound to the problem, but intuitively you can see that you can basically fix the length of B W, or length of, I mean, W transpose W would be the length of W. But you can fix W transpose SWW, which has to do with the length of W, and just search for the direction. Okay? So these two problems are equivalent. So if I want to solve this problem, what can I do? I can write Lagrangian, right? So Lagrangian, in terms of the primal variable and a dual variable, would be W transpose SPW minus lambda W transpose SWW minus 1. Okay, take derivative of the Lagrangian with respect to a primal variable and set it to 0. What's the derivative of W transpose SPW? Sorry? 2SPW. What's the derivative of this one? It's 2 lambda SWW. Right? And this should be 0. Okay. So it means that SPW should be equal to lambda SWW. Is this familiar to you? What is that? What would be the solution to this? Sorry? Eigenvectors of some matrix. And what that's some matrix? Sorry? Yeah, true. I can multiply both sides with the inverse of this one, for example. And so from left, if I multiply everything by the inverse of SW, then I have S inverse W, SB W is equal to lambda W. Clearly, this is an eigenvector problem, right? Because this is a matrix, and matrix times a vector is a scalar times a vector, same vector. It's eigenvector problem, right? So W would be eigenvector of SWSB. And lambda would be the eigenvalue of SW inverse SB. The name of this problem is generalized eigenvalue problem. Okay. A matrix times a vector equal to a scalar, another matrix times vector is generalized eigenvalue problem. Okay, SW is a noun, SB is a noun. So I can compute SW inverse SB and find the eigenvectors. Okay, what would be the dimensionality here? Don't forget that SB was d by d. SW is also d by d. So SW inverse SB is d by d. How many eigenvectors do I have here? Sorry? Okay, it's a d by d matrix, so at most there is d eigenvectors, if it's full rank. But is it going to be full rank? It's multiplication of two matrices. SW is summation of two covariance matrices. So it is full rank, most likely. But what about SB? What is the rank of SB? Sorry? 1. It's a vector times another vector. So the rank is 1. So here you have a full rank matrix times rank 1 matrix. So what would be the rank of this multiplication? One, right? So the rank of this quantity is 1. When the rank is 1 means I have only one eigenvector. Okay? So the rank of SW inverse SB is 1. There exists only one eigenvector. Okay, so in the case that we had two classes, we have only one eigenvector here. And that eigenvector would be the solution of our problem. So you can find that eigenvector, project everything on that eigenvector, and then classes are separated as much as possible. Any question here? Okay, when you have two-class problem, actually there is a way to solve the problem in a simpler way without computing, go through all of these computations. You know, a simple solution for two classes case. Okay, look at these equations. Let me replace SB with mu 0 minus mu1 times mu 0 times mu1. So I have SW inverse. Instead of SB, I just put mu 0 minus mu1 times mu 0 minus mu1 transpose W equal to lambda W. What's the dimensionality of W? What was the dimensionality of W?
D, right?
Sorry?
D.
It's D, right? So it's D by 1. It's a D by 1 vector because x's are from RD, right? So what's the dimensionality of this? What's the dimensionality of mu? It's d-dimensional, right? So mu 0 minus mu 1 would be d by 1. Mu 0 minus mu 1 transpose will be 1 by d. So here I have 1 by d, d by 1. This is going to be a scalar, right? So call this a scalar A or C. Call this a scalar C. So I can say SW inverse mu 0 minus mu 1 times C equal to lambda W. I don't know what C is, you know. I just know it's a constant here. But in fact, What I'm interested in is direction of W. I'm not interested in the amplitude of W, just direction. So I can say that, okay, I don't know what the C is, but this will tell me that SW inverse times mu0 minus mu1, whatever this vector is, it's proportional to this, because if I multiply this by C, it's going to be exactly equal to this, to the right-hand side. So when I don't have C, I know that it's proportional to this. When it's proportional means I know the direction, I just don't know how long this W is, which doesn't matter. I don't care. So, in fact, if I need to know W, in the case of two classes, I don't need to compute SW multiplied by SW inverse and then do eigendecomposition and find the first eigenvector. Simply, I can say that W is in the direction of SW inverse times mu0 minus mu. See, this is a vector. This is d by d, and this is d by 1. So this is a d by 1 vector. So this is the direction of vector W. And I don't care about the scale of W. I don't need to find exactly what W is in terms of scale, which is the eigenvector of this matrix. The direction can be computed this way. Okay, any question? Okay. So that was for the case that we had only two classes. What if I have more than two classes? So FDA for multi-class case. So now I have more than two classes. So in the two-class case, I had a projection matrix W. And we see that for two classes, there exists only one direction of separation. I mean, the final matrix would be rank 1, and there's only one eigenvector. So if you have two classes, there is one direction. If there is three classes, there's only two directions. If there are k classes, there's only k minus 1 directions. So for k class problem, there exists only k minus 1 directions. Okay. In the two-class problems, that was a vector, and I had this quantity, and I had this quantity. In the case that I have k minus 1 direction, let me replace this vector W by matrix W. Where this W, matrix W, is basically a matrix such that the first column is W1, W2, and the last one is WK minus 1 for K class problem. So it's K minus 1, D by K minus 1 matrix. Okay, we had two important quantities. Variance of projections within class and variance of projections between classes. You know, when it's a vector, W transpose SBW is a scalar. W transpose SWW is a scalar. When I have a matrix here, then, sorry, it's transpose. Then this quantity is not going to be a scalar, right? It's basically as if you do, you know, when you do this matrix multiplication, it's as if you do W1 transpose SBW1, and you do W2 transpose SBW2, and you do WK minus 1 transpose SBWK minus 1. So in each direction, you have a separate projection. But you are looking for the whole variance of all of these projections. Basically, the variance on this projection plus the variance on this projection plus the variance of this projection. So I can put simply a trace in front of this, which is going to be exactly the same as this value. If you are not sure, just write it down on the paper. Make sure that these two are the same. And the same thing will happen here. I can put a trace here. Okay? So here actually I had this maximization problem, W transpose SBW, which is going to be a trace of W transpose, which is a matrix now, W transpose SBW, divided by trace of W transpose SWW. And I want to maximize this. Everything goes exactly the same as this one, the same of the derivation that we had there. Exactly the same. So you write the Lagrangian, just you're going to have a trace in front of each of these. So you're going to have, basically, you're going to turn it to maximizing this trace, subject to the constraint that trace of W transpose SWW is equal to 1. You're going to write a Lagrangian. And you're going to take derivative, and derivative is going to be exactly the same. Because derivative of trace of W transpose SBW with respect to W would be SBW. There's a link on my web page in the part of resources. And there's a reference for matrix identities. So you can take a look at link. And in that link, there are derivative of trace with in the quadratic form, all functions of matrices and vectors. Quadratic form of matrices, cubic form of matrices, linear form of matrices, function of matrices, like trace of them determinant of them, and so on. When you want to take derivative with respect to different variables, what's going to happen. So if you're not sure, just consult with that link. It's going to be handy in your assignments, because it happens that you need to take this type of derivatives. But the derivative of trace of W transpose SBW with respect to W is going to be 2 SBW. So everything else would be exactly the same as what we have here, which I don't write it down. Okay. So the final solution basically would be eigenvectors of SW inverse SB. So SW inverse SB, you can show that has rank k minus 1 and has k minus 1 eigenvectors. Okay? So you have k minus 1 eigenvectors here, which is basically your direction of separations. The only thing that basically you need to know here is how to calculate SW and SB, because SW and SB in two class cases are sort of trivial. For W in two class cases, we had just sigma 0 plus sigma 1. Right? Now in K class problem, just add whatever number of classes that you have. That would be SW. What about SB? In two class cases, SB was mu0 minus mu1 times mu0 minus mu1 transpose. What if I have the third class? What I'm going to do? I have mu2 as well here. Sorry? A matrix with 3 columns? We want the distance between, in two classes, I wanted the distance between projected point of this class and this class to be maximum, right? I have 3 classes. I have to make sure the distance between projected points in these two classes are maximum. Between this class and that class is maximum. Between this class and that class is maximum, right? So it means that I need to add 2 terms here. That's between mu0 and mu1. I have to add some terms of mu0 and mu2 and some terms of mu2 and mu1. So you can imagine that how complicated it's going to be when you have k classes and k is large. Basically, you have to consider all pairwise cases between all of these classes and make sure that they are far apart. It's quite complicated, but there's a very simple trick that you can avoid this. And this simple trick is based on this understanding that the total variance of data is basically SB plus SW. So the total variance of data is either within class variance or between class variance. So I already know that SW is easy to compute. Now I tell you that ST is also easy to compute. So ST, when you have n data points, would be 1 over n sigma xi minus mu times xi minus mu, I equal 1 to n. And mu is basically just the mean. So just compute the covariance of the whole data. And since it can be decomposed to within and within is easy to compute, then easily you can compute between classes without going through this combinatorial problem of taking pairwise. Yes?
The total variance, I think it would make G different when n is large, but would you divide by n or n minus?
N minus d to make it, yeah, if you want to be correct, it's n minus d. Yeah.
Is there a transpose? First side.
Any questions? Okay, let me show you an example. Okay, this is a data set of images of handwritten images, 2 and 3. The size of this data set is 64 by 400. And there are 200, the first 200 images are 2s, and the second 200 images are 3s. Okay, so in this matrix there are 400 columns. Each column is 1 digit. Okay, so for example, if I look at, images are 8 by 8, which is 8 by 8, which is 64. So if I look at one of these images, for example, column number 10, and reshape it to 8 by 8, and then try to visualize it. Then that would be the result. Which is a 2, right? All first 200 images are 2. And after that, there are 3s. Okay? So we want to do PCA on this, and we want to do FDA on this, and compare the difference between PCA and FDA and this set of data. So first, let's do PCA on this data set. So to do PCA, I have X. I have subtract the mean from X, right? Centralize it, and then do singular value decomposition on that. So this is X, mean of X. Actually, if I just say mean of X, MATLAB will look at the mean of all of rows of the matrix, but they need mean of columns. So it's mean X2, okay, which is a vector of length 62. I want to subtract this mean from all elements of X, and X has 400 columns. Okay, so basically if I multiply this by 1s, 400, I have repeated this means 400 times, right? And then I can subtract it from X and call it X tilde. Then I can do singular value decomposition on X tilde. Now U is my principal components, and I have 64 of them. Suppose that I want to project everything on the direction of first two principal components. So my new space Y will be just the first two columns of U transpose times X tilde. That's my Y. Okay. Now, if I plot it, plot 1 in everything versus 2 in everything. Okay, this is this 400 points. I know the first 200s are 2s and the second 200s are 3s. So I just plot the first 200s that are 2s in different color, say red. Okay, here actually most of 2s are on the left hand, most of 3s are on the right hand. Okay? Let me use this plot image function that you are going to use in your assignment as well, and basically this function superimpose all of this handwritten digits on the top of this map. Okay, so we can basically visualize which point has been mapped to which two-dimensional representation. So this Y, two-dimensional Y, I want to see, that's the two-dimensional representation using PCA. That's my first principal component, and this is second principal component. Okay, so first principal component captured the identity of digits. Most of the digits on this part are 3. Most of the digits on this part are 2, right? And second principal components captured tilde. I showed this to you in the first lecture as promotion, as motivation, if you remember. So principal component captured the distinction between 2 and 3 because one of the variation of the data is difference between digits. Some of them are 2s, some of them are 3s. That's one of the variations. And out of the log, it turned out that the most dominant direction of variations is being 2 or being 3. That's why the first principal component captured this. Okay. Now let's do this with FDA. So in FDA, I'm going to define x1 as all points in class 1. So all x's that are 2's go to x1. All x's in the other class, which is basically 201 to the end, go to a different class. So what I need to do is to compute SW inverse and compute SW and find the eigenvectors. But in two class problems, I can do easier than this. I can only compute SW inverse multiplied by mu0 minus mu1. And that gives me the direction of projection. Okay? So direction of projection, I need SW. SW is basically summation of covariance of each classes, right? So covariance of x1. And MATLAB assume that rows are data points, columns are features. We assume the other way around. So if you want to use covariance, you need to put a transpose here. So the covariance of class 1 plus covariance of points in class 2, that would be SW. Now, if I find the inverse of SW, I haven't computed mean of class 1 and mean of class 2 yet. So I need mean of class 1, which is basically mean of x1. I need mean of class 2, and then inverse of SW times the difference between these two mean. That would be the direction of W. Okay. So W, this is W. Now W transpose times X is one-dimensional representation of data with supposedly, let me call it Y. Make distinction between points. So if I plot Y, hold on, plot Y, the first 200 in a different color. I don't know, can you see this at the back? No?
Can you make it a star or something other than just a dot?
Is it better now? The first two hundreds are 2's and the second two hundreds are 3's. This is one-dimensional representation, MATLAB show it this way, this is just the index of the point. Our representation is this one. Each point has been represented as one-dimensional point. So imagine that everything has been projected on that line, that all 2's are projected here, everything here is 2, everything here is 3. So there is a good distinction between 2 and 3. If you want to do classification, if you feed this scalar to a classifier, it's going to do a good job. Even you don't need a classifier, you just need to set a threshold here. Everything above this threshold is 3, less than this threshold is 1. Yes?
So is it always the case for FDA that the decision boundary is on the horizontal?
No. Here actually, we have two classes. And in two classes, always FDA project things on one dimension. So in one dimension, you can always have a threshold, right? If you have 3 classes, then you are in 2-dimensional space. And you have 4 classes, you are in 3-dimensional space. So the boundary could be anything. Boundary could be anything. Boundary is up to classifier. So let's visualize this the same way that we visualize the result of principal component analysis using digit plot. But for principal component analysis, we had 2-dimensional representation. Here, actually, I have 1-dimensional representation. I need at least 2-dimensional representation for digit plot to visualize it. So I'm going to manually add a dimension to this data. It's a 1-dimensional representation. See, my representation is y, which is 1-dimensional, 1 by 400. Manually, I'm going to add another dimension to this. So what do I mean by manually add? I'm going to define y, capital Y, such that the first row is y that I computed, and the second row is just 400 random numbers. So when I plot everything here, don't care about the second dimension. It's just random numbers. Just care about the first dimension. Okay? Now, so the second dimension make no sense because it is just random. But the first dimension, see, it's a very good separation between 3's and 2's. Way better than what we had in PCA. PCA was blind with respect to labels. It was just out of luck that the first principal component captured the identity. But here we guide the method to capture the identity. That's what's important for us. We give the label. So these are all 2's and these are all 3's. Any question? In this, you need to use this function in your assignment. Look at the code of this function. There's one line there, which basically I normalized the result of y. So that's just for the purpose of visualization. In some cases, when you normalize y, it gives you better visualization. But you can get rid of that line, and if it's not a good representation, which in some cases it's not, just don't normalize the result of it. Look at the code, you will see it, and you know what I mean. Okay, any question here? Okay, so if there's no question, I will see you next week. and we are going to start logistic regression.